Good afternoon, class. We are looking at Chapter 2 review, limits and derivatives, covering 2.1 to 2.8. Here's the part that part 2. We're going to cover Chapter 2, sections 2.4 through 2.6, 2.4, the precise definition, 2.5, continuity, and 2.6, limits at infinity, horizontal asymptotes. The precise definition, when we have the limit of f of x as x approaches 3 equals 5, what does it mean? It means f of x is close to 5. That means the y coordinate. When x is close to 3. As you can see, here's number 3. We are in the vicinity of 3 along the x-axis. We are in the vicinity of 5 along the y-axis for the y coordinate, also known as f of x. We can make the values of f of x within an arbitrary distance of epsilon. This is epsilon from 5, by restricting the values of x to be within the distance delta from 3, but x is not equal to 3. That's the concept of a limit. If x is between 3 minus delta and 3 plus delta, take a look. 3 is between 3 minus delta and 3 plus delta, then f of x is between 5 minus epsilon and 5 plus epsilon. Here's 5. Between 5 minus epsilon and 5 plus epsilon. By taking the values of x not equal to 3 to lie in the interval of 3 minus delta and 3 plus delta, we can make the values of f of x lie in the interval of 5 minus epsilon and 5 plus epsilon. And that gives us the precise definition of a limit. Somebody want to read the precise definition for us?
Let f of x be a function defined on some open interval that contains a, except possibly at a itself. We can say the function has a limit at a, limit of f of x when x is approaching a equals L.
Perfect. So if for every small number, epsilon is a small number, which is a positive number. There is a number delta. Delta is also a small number and it's positive, such that if the absolute value of x minus a is between 0 and delta, meaning the distance between x and a is extremely small between 0 and delta, then absolute value of f of x minus n is L is less than epsilon. That means the distance between f of x and L is extremely small, less than epsilon. So here's how we define it symbolically. So take a look at this one. We're going to read, this is whatever the value of epsilon larger than 0, there is delta larger than 0, such that if absolute value of x minus a is less than delta, that implies that f of x, the absolute value of f of x minus L is less than epsilon. So this is read whatever the value of epsilon. This means there exists and this means such that. Those are the symbols in math. I'm going to repeat that. Whatever the value of epsilon larger than 0, there exists a delta larger than 0, such that this line segment is such that if absolute value of x minus a is less than delta, therefore the absolute value of f of x minus L is less than epsilon. So if we are in this vicinity along the x-axis, we are in this vicinity along the y-axis, or we might see that we are projecting the x to f of x as follows, where x is somewhere between a minus delta and a plus delta, anywhere here. Then f of x is somewhere here between L minus epsilon and L plus epsilon. In this example, the value of L was 5, the value of A was 3. All right, use the graph to find delta such that the absolute value of x minus 3 is between 0 and delta. That implies that f of x, the absolute value of f of x minus 2 is less than 0.5. And I'm writing this general definition. And this general definition is the same as what you see here. Okay, you see this one. It's ultimately this. Now, guessing a value for delta given epsilon larger than 0, we need to find a such guess, okay, that it works in this manner. Well, let us start with f of x minus L less than epsilon. So in this case, we are here. Okay, so this one is this one, right? So we're going to write this. As you recall, if absolute value of x is less than a and a is positive, x is sandwiched between negative and positive a. So this way, this is sandwiched between negative 0.5 and positive 0.5. We are moving the 2, meaning we are adding 2 to all 3 sides. And we get f of x somewhere between 1.5 and 2.5. Again, the graph indicates that, but just wanted to show you analytically, algebraically. What are we looking for? We want to find delta such that this works. This is the distance for 2.6 to 3. This is the distance from 3 to 3.8. And delta is the smaller of the two, just to be on the safe side. So according to the graph, x is somewhere between 2.6 to 3.8. We choose delta to be the minimum of those distances. Look at this distance. Look at this distance between these two numbers. Look at this distance between these two numbers. And so this is 0.4. This is 0.8. And we choose smaller of the two. And any smaller number than 0.4 will do the job. And of course, x can't be 3. I want to make sure we understand why minimum of the two, because if you choose 0.4, even on this side, it works. But if you choose 0.8 on this side, it won't work. If I choose 0.8, it goes further down and it won't be within the interval of interest as far as the y coordinate or f of x is concerned. That's why you must choose the minimum of the two. As far as the proof, I'll go over an example to prove the limit of 4x minus 5 as x approaches 3 equals 7. You know that we just plug in. But as far as the proof is concerned, I'm going to show you one proof and the rest of them follow in the same manner. And I will start with this definition. We want to write out, we're going to write out this one. This is how you go with the proof. So replace the a with 3. Replace the f of x with 4x minus 5. Replace the limit L with 7. So first, the writing. The first one is the writing. The second one is that we start with this part and we basically get to this part. In essence, you're done when you do that, but we reverse the steps to show that this thing works, and that's a proof. So you always start with this part, the absolute value of f of x minus L less than epsilon. So let's start with this one. And as you can see, I can say 4x minus 5 minus 7 is minus 12. I can take the 4 out because the process is to get here, everybody. The process is to get here. And I want x minus 3. I found it, so I'm going to divide by 4. Now I'm going to put this one next to it. I'm going to put this one next to it. When I do that, because I want to compare to the absolute value of x minus a less than delta. X minus a less than delta for me is x minus 3 less than delta. This is identical, so this side must be identical. The choice would be that delta must be epsilon over 4. And in essence, when you find the relationship between the two, practically you're done. But we are going, the proof is that show this work. So how do you show this work? Reverse process, meaning now you start from delta and you end up with the f of x minus L. So the delta starts from here. If this thing is the case, how do I get to this part? Remember, I want to go from here to here. How do I get to this part? I'm going to make some changes. The very first thing I want to do, when we chose that delta is epsilon over 4, I'm going to multiply both sides by 4. So if I multiply, and remember 0 is not important because it doesn't change, right? So I multiply this one by 4, this one by 4, this one by 4. When I do that, this becomes epsilon. This is what I'm interested in. So I don't have to write this anymore. So I use epsilon. 4 times x minus 3 in an absolute value sign is equal to epsilon. And I'm going to take the 4 inside, make it 4x minus 12. Remember what I want. I want this. And I hope you see that 4x minus 12 is the same as 4x minus 5 in a parentheses minus 7. And when you compare that to this one, you see it's identical to that, right? So from here, we got here. So now that we got from here to here, we can write if the absolute value of x minus 3 is less than delta, we can take a look at those arrows. We can get to the absolute value of 4x minus 5 minus 7 is less than epsilon. And if you recall, from this limit we got here, that proves the limit works. The limit of 4x minus 5 as x approaches 3 equals 7. If we were to do the graph, x is approaching 3. So to the left and right of 3, we go by delta. The answer is 7, up and down by epsilon. And that's the proof. Continuity. A function has a limit at a if the limit of f of x as x approaches a to the left from the left is L, and that's equal to the limit of f of x as x approaches a from the right. If both sides are identical, the limit exists. Direct substitution property for polynomials or rational functions. If the function exists at the value a, then the limit of the function as x approaches c is equal to the function's value at a. Here's the limit of f of x as x approaches a equals f of a. In other words, it's saying that some of the functions, actually every function that we have studied in pre-calculus, it works as long as we are dealing with the domain, proper domain of that. A function is continuous if the limit of f of x as x approaches a equals f of a. A function is continuous from the right If the limit of f of x as x approaches a from the right is equals to f of a, and it is continuous from the left if the limit of f of x as x approaches a from the left is f of a. Can somebody read the IVT for us, please?
The intermediate value theorem. If f of x is a continuous function on the closed interval of a, b, and let n be any number between f of a and f of b where the two values are not equal, there must exist a number c in a, b such that f of c is equal to n.
Thank you. This is called the intermediate value theorem, and the bottom line is if you have a closed interval, and if you have a continuous function, not only it must cover everything from a to b, it's going to cover along its range as well. That's the concept, okay? All right, we want to determine c such that this function p of x is continuous at x equals 5, and p of x is defined as x squared minus 25 over x minus 5 when x is not equal to 5. It has the value of c when x is equal to 5. And right away, I hope you realize this means f of a 5 is c, okay? Or better yet, p of 5 is c. So let's take a limit. And to take a limit, we just deal with this because the function is always that except at 5. So that's the thing we are going to use. We're going to take a limit as x approaches 5. And I hope you realize if you plug in, you get 0 over 0. If you plug in, you get 0 over 0. This is a rational expression. The technique is factoring. And x is approaching 5, therefore must have a factor of x minus 5. There is no reason to factor, it's factored from, but the top is x plus 5, x minus 5 in any order. X minus 5 cancels out, and if you plug in 5, you get 10. So we found the limit of a p of x as x approaches 5 to be 10, and for it to be continuous must be equal to p of 5, which is c. Therefore, c must be 10. Show the function f of x equals sine x if x is less than pi over 4, cosine x if x is larger than or equal to pi over 4 is continuous on the interval of negative to positive infinity. And remember, a function is continuous at a point when the limit of f of x as x approaches a equals f of. Notice both of them are trigonometric functions. As you recall, the domain for sine is all real numbers. The domain for cosine x is all real numbers. So they are continuous from negative to positive infinity. Therefore, this is continuous from negative infinity to pi over 4. So the top one becomes continuous from negative infinity to pi over 4, and pi over 4 is not included. The bottom one becomes continuous from pi over 4, and pi over 4 is included to infinity. So the only thing that we have to check is pi over 4. So f of x is continuous everywhere except we don't know about pi over 4. And we must check it. So let us check the end point pi over 4. Again, I hope everybody knows that sine and cosine, they are continuous everywhere because the domain is. So let's take the limit of f of x as x approaches pi over 4 from the left. That means this function, right? Pi over 4 from the left is the top function because it has less than. And all you have to do, plug in pi over 4. As you know, sine of pi over 4 is square root of 2 over 2. I hope everybody remembers the common arcs. Pi over 4 is one of them. Now we're going to take the same limit, but this time from the right. That means we deal with cosine. The limit of f of x as x approaches pi over 4 from the right. That means the limit of cosine x as x approaches pi over 4 from the right. And that means cosine of pi over 4. As you know, it's also square root of 2 over 2. So therefore, the limit of f of x as x approaches pi over 4 exists, and it's equal to square root of 2 over 2. Now, we also know f of pi over 4 is cosine of pi over 4. Why is that? Because the equality is where it's going to give us the functional value. So the functional value is also square root of 2 over 2. This says the limit exists, and this says f of pi over 4 is square root of 2 over 2. We just prove the limit and the functional value are both the same. Therefore, f is continuous at pi over 4. If it is continuous at pi over 4 and it's continuous everywhere else, then it must be continuous from negative to positive infinity. Very straightforward class. We want to use the intermediate value theorem to show there is a root for this equation sine x equals x squared minus x between 2 and 3 included. And so remember the intermediate value theorem. First, we have to have a continuous function. If we move sine x to the right and say it's x squared minus x minus sine x, then we can move it to the left. Makes no difference, class. If you said you want to move it to the left and say sine x minus x squared plus x is just as good. And if you call this f of x, this is a continuous function, CTS, short for continuous, CTS. Short for continuous. Why is that? Because this is a polynomial of degree 2 or quadratic function. This is sine, it's a combination of sine. Quadratic functions are continuous everywhere from negative to positive infinity. So is sine, therefore the combination, because it's a combination of quadratic function and sine function. So because it's a combination of the two, it's continuous everywhere. And the given interval is closed. So all we have to find, again, I want to make sure we understand the concept here. If f of a and f of b were the two values that are not equal, then n be any number in between. We use this normally to show roots. Remember, if I can find a functional value, a y-coordinate which is negative, and another one which is positive, then when we say the root, that means in between, that means 0. So if this function can be negative somewhere in this interval, positive somewhere in between, then it must go through the x-axis. There must have an x-intercept. There must be a root. That's the concept. So sometimes it's easy to see. Sometimes it's just by inspection. If I go with by inspection, f of 1 is less than 0. Why is that? Let's plug in 1. When you plug in 1, these two cancel each other because 1 minus 1, you get negative sine 1. And I hope you know that negative sine 1 is a negative value, because when we say 1 is 1 radian, so about 57 degrees. So sine of 57 degrees, negative of that. We don't know I mean, we can use a calculator. but we don't have to. We know it's negative, and that's all that matters. On the other hand, if we use f of 2, we know it's positive. Why is that? Let's plug in. If you plug in, 2 squared is 4, 4 minus 2 is 2. So 2 minus sine of 2. Now, sine of 2, you may not know what it is, but worst case scenario for this case is positive 1. So 2 minus 1 makes it 1. So this is positive, everybody, always. So this is always positive. Therefore, since 0 is between f of 1 and f of 2, right? 0 is between negative and positive value. IVT applies, and f of x is continuous on the interval of 2 to 3 and has a root in between. All right. Limits of functions at infinity, horizontal asymptotes. Here's the definition. Horizontal asymptotes of the curve y equals f of x have the equation of the format y equals L. If the limit of f of x as x approaches minus infinity is L, or the limit of f of x as x approaches positive infinity is L. Okay. The limit of 1 over x as x approaches infinity is 0, so y equals 0 would be the asymptote here, the horizontal asymptote. This is also 0 when p is larger than 0. Those are some theorems that are pretty straightforward. You should know them. This is a basic exponential function when the base is larger than 0. For example, y equals e to the power of x. And this one is exponential growth. This one is exponential decay when b is between 0 and 1. For example, y equals e to the power minus x. So in this case, the limit of e to the power of x as x approaches minus infinity is 0, and therefore y equals 0, or the x-axis, is the horizontal asymptote. And of course, when x approaches infinity, y goes to infinity. That's, we're talking about the first quadrant. X goes to infinity, so does y. When we say limit of f of x as x approaches infinity, this refers to the y coordinate. In essence, it blows up. For this case, the limit of e to the power minus x as x approaches infinity is 0. So again, we still have the same x-axis, or y equals 0, as the horizontal asymptote. But this time, the limit of f of x as x approaches minus infinity is infinity. In other words, when x goes to negative infinity, y blows up to positive infinity. And everybody remembers the basic cube function, y equals x cubed. The limit of f of x as x approaches minus infinity is minus infinity. We are referring to the third quadrant. And the first quadrant indicates that the limit of f of x as x approaches infinity is infinity. I hope everybody remembers this stuff, and I can't emphasize the importance of understanding the concept of a graph, because it will help us remember everything, okay? So horizontal asymptotes, again, vertical asymptotes. And I want to remind you a very important function everybody is familiar with, logarithmic functions. For example, y equals ln x looks like this. As you can see, the limit of this function as x approaches 0 from the right is negative infinity. I hope you see that. Therefore, the vertical asymptote has the equation x equals 0. So reminding everybody that in order to find VA, you look at the function and take a limit when x approaches a, or a from the left or a from the right. Any of them is infinity or negative infinity. That gives rise to x equals a being the VA, or vertical asymptote. Here's an example of a case that has two horizontal asymptotes. In this case, it's the tan inverse. The limit of tan inverse of x as x approaches minus infinity. When we go this way, it goes here to minus power 2. When we go to the positive side, the limit of tan inverse of x as x approaches positive infinity is pi over 2. In other words, you may remember tan of power 2 tends infinity, tan of negative power 2 tends negative infinity. Let's look at some of these limits. And as you recall, just to find the limit, I'm going to remind you, you plug in, if it gives you a number, you're done. 0 over any number other than 0 is done. Number over 0, we looked at a case where we figured out infinity or negative infinity. And there are many, many, many forms of indeterminate forms. These are some of them: 0 over 0, infinity over infinity, infinity minus infinity, and things like that. Now, anytime you're dealing with a rational function, and t is approaching infinity, you divide by, the technique is to divide by highest degree term in the denominator. So we divide everything by t squared. And we simplify. And I hope you realize we are carrying the limit sign. But now, if you actually evaluate the limit, for example, the limit of this as t goes to infinity, this is 0, 0, 0, 0. Everything is 0 with the exception of 1. And I want to keep it that way because I want to make sure everybody can see this is 0 over 1, which makes it 0. In other words, you need to know the denominator is not 0. What about this case? Again, we have a rational function. And again, t is approaching infinity. This time, we do the same thing. We divide by highest degree term in the denominator, but that one is t. And let's do that. Divide everything by t. Simplify each term in the numerator as well as the denominator. And now apply the limit to each piece. This is infinity, this is 2, this is 7 over infinity, 0, minus 5, 0, this is 0, this is 0. Now, please understand, infinity plus 2 or plus 20,000 or minus 20,000 is still infinity. And when you divide by any number, it is still huge, but depends on the sign. So because this is minus 5, this becomes negative infinity. And that's something you want to be careful of. If we had infinity divided by, let's say, positive 5, it would be still infinity. Or for that matter, divided by 50 billion, it's still infinity. But this one, you want to be careful with the sign. And you may remember from pre-calculus, the degree of the numerator is smaller than the degree of the denominator, you get 0. If it's larger, it goes to infinity or negative infinity, or you have slant asymptote or oblique asymptote, if you recall. For this case, I hope you realize if you plug in, you get infinity squared plus 1, the square root of that. This is infinity, everybody, and so is this one. So you have infinity minus infinity, which is indeterminate. And I want to make sure that everybody understands infinity minus infinity is not necessarily 0. It can be 0. It can be infinity. It can be another number. It's indeterminate. You have to figure it out. And the technique is the conjugate because it's a square root. So you multiply by the conjugate, changing this to a plus, and you also divide by it. So you have this expression, which is equal to 1. Please understand this expression is equal to 1. This is equal to 1. And so basically, you keep the denominator, you multiply the top, you multiply these two, and it squares the first one. Minus squares the second one. And this is what you get, okay? right? And now if you plug in infinity class, the denominator is infinity plus infinity, and so 1 over infinity is 0. It happened to become 0. Doesn't happen always. I'll show you in a moment that it's not going to happen always, okay? Zero. Let's continue with the limits. And in this case, all you have to do, plug in. I hope you realize this part, e to the power minus infinity is 0. And here's the reason. A to the power of minus m is 1 over a to the power of n. So e to the power of minus t is 1 over e to the power of t. And 1 over e to the power of infinity is 1 over infinity is 0. 12 over 4 equals 3. What happens to this case? If you plug in, the numerator becomes infinity because it's 5 plus e to the power of infinity. And the denominator becomes minus infinity because it's 4 minus 3 times e to the power of infinity. And although it's not a rational expression, we use the same technique and we divide by, remember, in the case of a rational function, we divide by highest degree term in the denominator. Now, we're going to divide by the highest value in the denominator, which is e to the power of t, and it simplifies as follows. If we replace the t with infinity, this goes to 0, this goes to 0, 1 over negative 3 or negative 1/3 is our final answer. If we plug in, we get infinity squared minus infinity. Simply put, infinity minus infinity, which is indeterminate. So we have to use some sort of an algebraic technique, in which case is factoring. So when we factor the x out, now, as you can see, this is infinity minus 1. Infinity minus any number is still infinity. Their product is infinity. So I hope you remember. In the previous page, infinity minus infinity ended up 0. In this case, ends up with infinity. And in some other cases, you'll find out that it gives you some other number. You're dealing with a rational function. And x is, whether approach infinity or negative infinity, the technique is the same, which is division by highest degree term in the denominator, namely x. Divide everything by x. Now, replace it. This is infinity, this is 1, this 3 over infinity is 0, minus 1. Now, here's what I want you to be careful again. The numerator, infinity plus any number is infinity. The denominator is negative 1. That's why you want to be careful. It's negative infinity, class. You want to be very careful with the sign. Okay. Negative infinity. We want to find the limits, starting with the limit of e to the power minus x plus 2 cosine 3x as x approaches infinity. We can separate them into two pieces. And this one doesn't exist because this one is e to the power of minus infinity, and it goes to 0. But this is the one. The limit of sine or cosine as x approaches infinity, that doesn't exist. Why? Because it oscillates or alternates between negative 1 and 1. As you recall, the range for a cosine function is negative 1 to 1. So it's always between -1 and 1. So the limit of cosine, doesn't matter what the, or sine, doesn't matter what the argument is, as x approaches infinity, does not exist. And that's the reason. What about this case? Remember, this is not a rational function because the top and the bottom are not polynomials. But the technique is still the same. Divide by highest value in the denominator. Remember, in the case of a rational function, we divide by highest degree term in the denominator. Now we are going to divide by highest value, which makes it e to the power of 3x. So when we divide everything by e to the power of 3x, this one and this one become 1. I hope you know when you divide this one by this one becomes e to the power minus 3x, which is e to the power of minus 6x. Since x is approaching infinity, this goes to 0, this goes to 0. The answer is 1. Okay, everybody. If it helps you see it better, you can change this to minus 1 over e to the power of 6x. The same thing for the bottom. So when x goes to infinity, this goes to infinity, 1 over infinity is 0. Okay, so what you are dealing with in essence, it's 1 minus 0 over 1 plus 0. Okay. Let's look at an interesting question. We are interested in finding the limit of tan inverse of ln x when x approaches 0 from the right. Well, because tan inverse and ln are both positive functions, we can, and the limit applies to x, we can interchange them and put the limit here in front of ln x. It makes no difference. And what is this? I hope you remember the graph. This is what? Minus infinity. We want tan inverse of minus infinity. There are two ways to approach it. First of all, you remember this graph of basic tangent, one complete cycle. X equals pi over 2 and x equals minus pi over 2 are vertical asymptotes. So when x goes to pi over 2, y goes to infinity, right? When x goes to negative pi over 2, it goes to negative infinity. So the answer is negative pi over 2 according to that. Or if you look at the graph of its inverse, this one is y equals tan inverse of x. Either way, the answer is negative pi over 2. The second method that I wanted to mention is that if you said this, I'm going to write it here, tan inverse of negative infinity is x, then by definition means tan x is minus infinity, and therefore x is minus pi over 2. Okay, x is minus pi over 2. I don't know which way is easier, but that's really the methodology. Here's the next question, and this is a very complicated question, so I hope it reminds you of the squeeze theorem. And so what we need to do, we need to start from somewhere and make it look like that. And as you know, since it involves sine and cosine, start with sine, sine in between negative 1 and 1. When you square it, please understand, squaring this is positive 1. You can't say it's between 1 and 1. No. Think about this. If it's 0 and you square it, you get 0. If it's between -1 and 0, this is the answer. If it's between 0 and 1, this is the answer. If it's between -1 and 1 is the answer. We want to make it look like that. So let's divide everything by x squared plus 1 or multiply it by 1 over x squared plus 1. And by the way, x squared plus 1 is a positive value. Everybody knows that because we have a plus 1, okay? And x squared is 0 in the worst case scenario, otherwise positive. So let's multiply everything. So this doesn't change, this will change to this, and this is 1 over that. Let's take a limit of this function as x approaches infinity, which is 0. Let's take the limit of this function as x approaches infinity, which is also 0. So this is 0. This one, when x goes to infinity, what happens? This goes to infinity, 1 over infinity is 0. And therefore, this limit by the squeeze theorem becomes 0. The limit of sine squared over x squared plus 1 as x approaches infinity is 0 by the squeeze theorem, ST, squeeze theorem. Reminding you of definition for horizontal asymptotes, vertical asymptotes, we want to find those. To find the horizontal asymptotes, we're going to take a limit as x goes to infinity or negative infinity. And because it's a rational function, they have the same methodology, namely divide by highest degree term in the denominator, which is x squared. So divide everything by x squared. So what happens? This becomes 2, this becomes 3, this becomes 1 over x squared, this becomes 2 over x, this becomes minus 1 over x squared. And this goes to 0. Everything goes to 0 except those two. So the answer is 2/3. What does it mean? Horizontal asymptote y equals 2/3 is the answer. So we found the horizontal asymptote, everybody. What about the vertical asymptote? The limit of f of x approaching infinity or negative infinity as x approaches a. Simply put, set this one equal to 0 and solve. I hope you realize 3 is a prime number, is 3x and x. -1 is just 1 and -1 in some order. Set this one equal to 0, x is 1/3. Set this one equal to 0, x equals -1. We have all the horizontal asymptotes. There are 2 vertical asymptotes. We are done. Finally, for this part, we want to find the formula for a function that has a vertical asymptote of x equals 1, x equals 3, and the horizontal asymptote of y equals 1. And please understand this is not necessarily unique, but here's one easy way to find it. Because one of the vertical asymptotes is 1, we're going to say f of x, this is one possibility, f of x has this form, the denominator must have a factor of x minus 1. This is another VA, so must have a x minus 3 factor in the denominator. Okay, now, since the horizontal asymptote y equals 1, that means the degree of the numerator, because this is 1, degree of the numerator must be the same as the degree of the denominator. As you can see, the denominator is x squared minus 4x plus 3. So this must have some sort of x squared at top. And because it's 1, the coefficient must be the same, so we can put x squared. However, why am I saying this is one possibility? If I have something else here, let's say plus 2x, I'm just making it up. If I have plus 2x, nothing changes. I still have the same VAs, vertical asymptotes, the same horizontal asymptote, okay? Just as an example. Or I add another, I don't know, constant, let's say 5. Things don't change. And that's why you want to be aware of that, okay? So there are, in essence, infinitely many solutions.